So this is where we were yesterday evening. And what I was saying is that, phase portrait is one of the representations of how the system behaves when we plot one of the variables with respect to the rate of change of that variable, right? And for a two dimensional system, you can see that, it's going to be, as I've shown you here, bottom. And this is a linear system. It's a very classical system which is used for the illustration of this kind of problem. And what we find here is that if we have a Hookean spring with k equal to 1 and a mass equal to 1, then the trajectory just depends upon the initial value. So if x is equal to x0, let's say if x0 is this one, then it will be one circle like this. If x0 is this point here, then that is another circle there. Okay. So this is nothing but a simple harmonic oscillator. Okay. Now what I'm going to do is I'm going to take you through 2-3 examples where we discuss how to draw something on the phase plane. Okay. Can anybody tell me why we draw something on the phase plane? Yes. Anybody?
Or to analyze about the stability of the system?
Stability of the system, correct. So, so what we are doing is we are looking at, and I'm always trying to draw a parallel with the control theory or the systems theory with what we are going to be doing later on when we're looking at gene regulatory networks. So what we are saying is that there is this huge knowledge of how to deal with information in networks of systems which are electrical or mechanical or chemical, and they are at the macroscopic level when this was developed. But that knowledge can be easily drawn into the level at which gene circuits are actually present in cellular systems. And so that how to apply that is becomes important. And what we were discussing yesterday was that whenever you look at two different states of a microorganism, let's say a wild type versus a phenotype with a certain property, then there are certain changes that have happened. So if you made that change willfully, you would have known where exactly that change was made. Let's say you were looking at the TCS cycle and you made a change in one of the enzymes or one of the gene regulations that took place in the TCS cycle. You wouldn't know exactly what has happened, right? So in that way, you can reconstruct that network and compare the wild type versus the phenotype. And one of the ways to understand what's happening is to look at what has happened to the stability of the system. And if you write out the equations, it's much more easier to understand because now you have got the tools that discuss stability. The stability analysis as such, when you are doing it in using mathematics, and then there is a very standard procedure that is there. You look at what is called a characteristic equation, you solve it for the roots, and then you can talk about the stability. Sometimes it's not so apparent, and especially for large complex systems. And for large complex systems, you may not be interested in all the variables that are there. You might be interested in one or two of these which you think are critical to that. And when you pick up those one or two variables, how do you understand what has happened in that? So if you made a phase portrait of that, then you could easily understand what's happening. So when we talk about stability, we also have to talk about phase portraits. There's just no way that you cannot discuss these two items together. So what I'm doing now is taking you to the next step, which is looking at phase portraits to understand what's happening. Because just by looking at the nature of the phase portrait, you can come up with some intuitive ideas about what is the quality of stability. Okay. So with that in mind, I'm going to take this part of the lecture in two parts. One is to show you analytically and graphically how this can be taking place, and the other, of course, is using a proper solution, solving the equations and all of that either numerically, and one of the tools that we have been discussing yesterday was the Simulink, which is part of MATLAB, or you can do the coding. That's also fine. Okay, so I'm going to do it in 2 steps. So let me get back to the slides. And here, what we first thing you need to understand is that you have to understand what are singular points on the phase plane. So these are the points at which the system is in equilibrium and points at which the system can stay forever. Okay, and the way you find that out is just by setting the rate derivative or the time derivative of that to go to 0. So as you can see here, if x dot is equal to 0, then you get 2 things that are going to happen here. From the previous slide where we had these equations, you're going to get fx1 x2 equal to 0, as well as f2 x1 x2 is also equal to 0. And you could actually also do another manipulation, which is divide the second equation by the first, and you also get, in that case, this ratio of the 2 derivative of the variables in the phase plane with respect to and that comes in terms of the functions that are defining those rate changes. So you can see that dx2 by dx1 would be f2 by f1, where f2 and f1 are functions of x1 and x2. Now let us look at a very simple example. So this simple example is of a first order system, and this first order system, is it linear or non-linear?
So non-linear.
Non-linear, correct. So it's non-linear. So be very sure about these things, because if you don't understand, then you have to work out. So non-linearity can come because of the way the derivative is defined, or the way the functions are defined on the right hand side. So either way you can get. So here we got the cubic term here, which makes it non-linear. Now when you solve for this, you'll get x is equal to 0, x is equal to 2, and x is equal to minus 2, which is clear from this equation. So you have got 3 points on this axis, which would be the zeros. So one point is on the left hand side, which is this point, minus 2. The other one is on the right hand side, which is plus 2, and then 0, which is at the center right here. And if you were to plot this x versus x dot, then you'll find that this point, which is there, 2 and minus 2, they are going to be unstable points. And so this is, although we said that it is a point at which the system can stay forever, it's not. It's also true that sometimes you get situations where you have instability at those very points. That means those points would be quasi-stable, and they would be stable as long as there's no perturbation. The moment there's a perturbation, it'll move out in one of the 2 directions that are shown here. So this point is actually the node, as we call it, which is going to be stable. So if you perturb it here and the perturbation is towards the left, it's going to move here. If you perturb it here and the perturbation is to the right, it will move here. If the perturbation is to the right here on this side, it will move out. If the perturbation is to the left on this side, it will move out. So this is one of the ways that you can. So you can see that a simple picture like this, with the arrows showing what is the direction in which the movement is going to take place, will give a very simple idea of qualitatively how the system is going to behave. Just like I mentioned while I was explaining this. So also keep in mind that there is symmetry when you look at these phase portraits, and the symmetry can be 3 kinds. One is about the x-axis, in which, keeping the x fixed, the image is reflected upon the y. So whether x2 is equal to negative or positive, you'll have images on both sides which are going to be symmetric. Then similarly, if this is about the x2 axis, then keep the x2 axis fixed. Then x1 and the reflection of x1, which is the negative of x1, is going to be the same. And if it's about the origin, then it does not matter. Either way, you can fold, and you'll get symmetry. So this is something that is important, because as you work with larger systems, then your domain of analysis can just be very simple. So if you find the solution is easier to do, let's say in this domain, then you don't have to worry about the entire domain. You know right away, well, all I need to do is just draw the reflection of that, and that's going to work out. But of course, you have to make sure that this is proven first when you buy analytical methods. Clear? And also note,
Yes,
yeah, good. So also note that here we have another definition of this that I've given here from the previous equation, where we looked at dx2 by dx1. Here there's a negative sign and here. This is also called an initial slope for starting or drawing the phase portrait. Whenever there's a negative sign by the division of x2 and x1, which are the two coordinates, two axes of representation on the phase plane, then the negative sign will mean it will go downwards, and a positive sign means it will go upwards from that point. So whatever is the equilibrium point that you get, then at that equilibrium point, this is the way the behavior is going to take place. All right, that's the other thing that I wanted to say here. And now we're going to look at, like I said, two methods. Analytical method, we'll just see how to do it. So all you do is you just solve the equations and then eliminate the t and you work it out. So t becomes a parameter and you can work it out. But you can also do numerical methods as part of subgroup of this analytical method, because all you're doing is solving this. But the isocline method is a graphical method, and this we are doing because it's of academic interest. The reason it's being done here is that by doing one such example, you get a very good understanding of how the whole thing works, and it is something that, or a method that actually gives you the knowledge, of how these phase portraits actually really work. And so here also the first method is to eliminate t, then to obtain the equation for the isoclines, and then plot it on a phase portrait. Okay. So let us look at the analytical method for the first example that we have done here. So here we know that m is equal to 1, k is equal to 1, and then you look at the equations. So x double dot plus x is equal to 0, and at x equal to x0 and t equal to 0, you can find the solution. And the solution for the system is very well known. X0 cos t, and x dot is equal to derivative of that, so minus x0 sin t. So that automatically tells you that, if you were to just work this out, then if you represented x dot as x as x1 and x dot as x2, then x1 squared plus x2 squared will be x0 squared. That's what we can see here. And so it clearly tells you that it's going to be a series of circles depending upon the radius x0. So the initial condition defines the radius. So if x is equal to x0, that is the radius. So based on a radius, you can draw a circle. So that's the analytical solution. Clear, very easy to do. Okay, now we look at the method. So that's how we would solve it actually also when you were doing, if you were to do. So what you can see is that, we essentially get the solution of this by looking at the equilibrium points, look at the initial condition, and then use that set of equations that we get to solve for, to eliminate the t that is between the two. So eliminating t, this is what we had got. So the method is to make parameterize in terms of t. Okay, now look at the method of isoclines. Now method of isoclines looks a little cumbersome, but like I said, this is academic in nature, so it's good to follow through one such example, and maybe do one hands-on with yourself, and then you can because this is no longer a technique that would be used if you, for example, if the person had an access to MATLAB. So this was all done historically to do something quickly when computational methods were not strong enough. But anyway, so I am just putting this as an illustration. So the first thing that you do is, of course, you work out the linear form, you define it, then you determine. So when you do this, you can divide x delta dx2 by dx1. So you can then, of course, the next thing that you do is you look for the equation of the isocline. Then there may be some symmetric properties, so work those out if you have to. Then you look at critical and stationary points, and these will be, some systems will of course have multiple stationary points, so you can work those out. And if there is this couple first order, then you'll have to look at requirement of each equilibrium point, perhaps, if it is just depends upon how many groups are being coupled here. And then you can also look at what is called, you'll have to also determine what is a null line for the system, and then construct the global phase portrait. So we'll talk about this. So let us look at one such example. And the example that I'm going to do here is the van der Waals equation. And we'll also look at how to do this in Simulink later. Okay. Now, the van der Waals equation is one of those oscillators which are traditionally has been used by most system theory work, where you want to essentially understand how oscillations in a system are being changed or controlled, or you want to find a system like that and then define some other uh, analysis that you worked out or new methods that you worked out to see if it works out on something that is very well known. So this is a very classical system, and what you can see is that you could break this equation up into two variable equation by just defining a transformation of variables, and then if you divide this, then you get on the right hand side this, which is f2 divided by f1, which is x2, and there's a negative sign in front. So now you see what you do is you parameterize this and use a parameter called alpha, which is going to be what we call the slope of the. So this is how you derive the slope of the equation of the isocline, and this would be the slope of alpha of the isocline. Now we'll talk about this a little bit more, but first let us just see this part of the equation, which is the function and the alpha. And if you just rearrange it, you will agree that you can get this equation out here, right? So the negative sign is here, so I could change the negative sign there, minus it and bring it back here. So this whole thing is very simple. Okay. Now, if there's any a priori symmetry, then we can look at that also. So we can see for this one, if this is not there, then there is no symmetry in this. So there's no way you can find any symmetry. So we see that there is no symmetry there. Then you look at the critical stationary points. So x1 dot equal to 0, x2 dot equal to 0, and this gives you one stationary point, x1 equal to 0, x2 equal to 0. So now we have to construct the isoclines. How do you construct the isocline? Well, we got that equation, so use that equation to do this. And maybe what I'll do is I'll just try to use this board once again to try and kind of show you how to do this if I can get a hang of this one. So far, any questions from any of you?
Sir, for drawing isoclines, we will have to choose a specific x1, x2, right?
Sorry?
Oh,
Loudly,
like
loudly.
for drawing or like isoclines, we will have to choose our own arbitrary x1, x2.
Yeah, you have to have your own arbitrary. One of them will be arbitrary. So depending on how you are writing the equation. So if you're making x1 independent, then x2 will be dependent. So way you formulate the equation. So we'll see that in a minute. Oh, why did I do that? Fine, that's okay. So anyway, let me just see. Whenever I need to use this, I'll use this. Okay. Let's look at this equation here. So now, what is the meaning of alpha? Anybody has done this before? To tell me a little bit, if you know, else I will explain. Just one of you can tell me whether this has been done before or not, or you've come across this before or not.
No, sir, this is the first time.
Okay, fine. So let's talk about this alpha. So to illustrate that, let me just go forward. I think there is an equation here. So what I'm going to do is, maybe for this class, I'm going to just pick up those equations if I can. Just to illustrate what's happening here. I'm going to place it here. Okay. I'm just placing the equations here. Okay. So what it means is that why is it not responding? Maybe I should restart this. Yes, let me just make sure that this is understanding that is here. I don't know why it's not working today. Anyway, I'm just going to use my. Always have a difficulty with this. So, so what I was saying is that I wanted to say something now. I got distracted. Let me just quit and restart. Okay. So bothering. Anyway, so so we have this van der Pol oscillator here, and we have this. So these are the equations that are defining van der Pol oscillator. So essentially, what you do is you write out the equations with one of the variable as an independent variable, the other one as a dependent variable. Here, x1 is the independent variable, and x2 is the dependent variable. So what it means is that that this equation that I have here is going to be the equation for the isocline. Where is the alpha? Okay, I already had predefined the alpha here. So if I put alpha equal to 0, then I get this equation. Alpha equal to 1, I get that equation. Sorry, minus 1 and alpha equal to 1, I get this equation. And if you go back one more step, I need this other equation also, which I'm going to bring back here. I'm going to skip. How do I bring back this one? Okay. So I'm going to take this equation also, Control C, and bring it there. It's important for you to see this equation. Okay. So all of you can see this equation also. Now you see here, this is the equation of the isocline. So so what you're saying is that whenever I look at a small slope on, whenever I look at a small slope on the curve that I've drawn for the van der Pol in the phase portrait mode, that means with this being x1 and that being x2, let's say. Okay. Then at any point, dx2 by dx1 would essentially tell me the slope at this line. Now the question I have is that if I had multiple of these curves drawn for different initial conditions of x1 and x2, so this of course has been drawn with one particular condition of x1 and x2, right? So, and that condition would be if you could pick any one point on this curve, let's say this point, this would be just as good as this point on this curve as an initial condition to generate this circular curve on the x1, x2 plane. Clear? Now, so that would be, so there would be several, I mean, you could pick up so many different initial conditions just to give you this one curve. Now, in this entire state space of x1 and x2, you could also have an initial condition there. You could also have an initial condition there, right? So the question is, if all of these initial conditions were drawn, then what are those curves where the slope would be exactly the same? So dx2, dx1 would be exactly alpha. That's the question you're asking. So in this case, it is predefined. So alpha equal to 0 is the first one. Alpha is equal to 0 here. This is the first equation. So if I set alpha equal to 0, I can see that I get this equation very easily. X2 is equal to this whole term, this whole this negative of this divided by this whole term here. Very clear to see. If alpha is equal to -1, then all I do is I just replace this by -1, and I can see that term will come here. If alpha is equal to +1, then that plus term comes here later on. So you can see, depending upon this is where the alpha is coming, right? So those alphas are there. Now, so if alpha is equal to 0, it means that no matter how many of these curves I draw, then if there was another curve starting with another initial point, when it comes to this particular line here, is going to have a slope of 0. So the isocline is the locus of all the points where a van der Pol oscillator would have the slope 0 if it started with different initial conditions. Clear up to this point?
Yes, sir.
Okay.
Yes, sir.
Similarly, it would have a -1.
Yes.
So this would, the isocline would be the locus of all the points where the van der Pol oscillator would have a slope of -1. And this would be the slope of all the lines. Sorry, this would be the locus of all the points where the van der Pol oscillator will have a slope of +1. And so once you draw the locus of those points, you join it, you get what is called the isocline. So this is an isocline with alpha equal to 0. Isocline, so let me use this one. So this is isocline with alpha equal to 0, right? As the first equation. This is the isocline with alpha equal to -1. Okay. And so on. So and now you can see that I could have a high density of these points, right? So I'm going to see if I can get rid of all of these points now. What I've done. So okay, I don't have any erase. I have an erase here. Fantastic. Okay, so that's what I would get. Okay. Now, if you can imagine that if I made this x2, x2, x1, x2 plane dense enough with all these isoclines, starting at any point, I would be easily able to see where my next point will come, right? And if I join it, then I'll get what is called the van der Pol oscillator. So for a given initial condition. So the reverse problem is what you're trying to do. So the way it was done is that you reverse it and you get the way to construct this. So let us look at this one here. So this is very easy, and because this is it's a regular figure and you have symmetry, so all you needed to do maybe just construct this quadrant, you would have got the answer. So you can see it is going to have an initial condition which goes downwards and then goes upwards. Alpha equal to 0, alpha equal to 1, alpha equal to -1, and so if I have this point, then the next point will be here. We're going to have infinity slope is going to go have a 0 slope, again infinity slope. So one is a plus infinity, one is a minus infinity. So it's going to go this way. Okay, clear? Now let us look at an example here. So this is an example of a system where there's a reaction taking place, and of course I will not. So all of those things
Sir,
have been taken care of. Yeah.
sir, what is this Van der Waal oscillator? Like, what's the meaning of like that? What is
No,
this
it is just
case?
nothing. It's a Van der Waals oscillator is attributed to the person Van der Waal who wrote out an equation of this kind, such that this would give you an oscillation. And the way you can change the nature of the oscillation is by just changing this parameter 2, 0.2 given
Sir,
here. If you change this parameter 0.2, you will get a series of these oscillators which can be used. And the purpose of having an oscillator like this is that you can do all your studies. So if you know that you have an oscillating system, or you want to test out something on an oscillating system, one of the good things to do is to pick up a Van der Waals oscillator and just check out. So if you have this equation, then if you wanted to see if you could do some work with it in where you need to look at stability and other things, then this oscillator would be a model system to look at, because
okay,
it's very well defined and a lot of people have worked on it. So that's the reason why you pick up this one always. Okay,
okay, sir,
clear?
understood. Understood. Yes, sir. Yes.
Okay. So now I'm going to give an example of another system, and this one you need to follow carefully. So this is of course a second order system, but linear, and you can see that the first order is dependent on the second derivative, second variable, and the first rate of change of the first variable is dx1, dx2 is dependent on the second one, which is x2, and x2 is dependent on both, and there are negative coefficients -5 and -2 for x1 and x2 respectively. Okay, so we do the same construction all through. So first we look at the right hand side and both, and so if I divided x2 by x1, then I'll get the negative of this term coming here, the negative components which are here, 5 -5x1 -2x2 divided by x2, which is there, and we say that let that equal to alpha, then this becomes the equation for the isocline, which if you resolve this and make x2 the subject of the formula, then you'll get in this fashion. Now you look at the initial point. So there is an initial point which is already given to you, x1 by x2. So if you looked at dx1, dx2, and you divide this x2 by x1, then you see that this is going to be a negative slope, negative infinity. So it will go downwards from the point 1, 0 as the initial trajectory direction. Clear? So that's how you get the initial direction of the trajectory. So how do you construct this? So I'm not to keep the figure clean. I have not shown the hash lines to show what the slopes look like, but this is the slope with. So you can see here. So this is going to be the slope with minus infinity. Then this is another high slope of 10. Then this one is going to be a slope of 3, and so on. So and the slope of 10 will be on this one, and the slope of 3 will be on this one, and the slope of infinity will be on that one. So it will be, what I've not shown is I've not shown you these hash marks like this, like this, like this, which has shown in the previous one. But that is something that you can draw. But I've just shown it about the point that is appearing. So so what you do is essentially by starting at the point 1, 0, you know that it's going to go downwards. But you also know that when it reaches the next isocline, its slope should be 10. So usually what is done is at this point, for piece of construction, you draw both the slopes, minus infinity as well as 10. And then draw the line in such a way that if there were hash lines here, you could see how this would come, and when it touches this point, it starts off being vertical and then curves in so that it becomes minus 10 at this point. Sorry, plus 10 at this point. Okay. So that's how this is. And then as you go downwards, so between this and this, it should have a slope of 3 here, and it goes down like that and continues. So you can just look at the animation of this. I had done this, so this is what it will be. So you can start off by the construction of that, then and you construct the next slope of the next isocline, and then kind of draw a midpoint going through it. More or less, you'll get the right answer. Then you start from this point, you draw the next slope, which will be parallel to the second slope that you have drawn here, which means that this slope and this slope are parallel. Then you draw another line there, which is going to be slope of 3. Then you draw the midpoint, and you continue in this fashion, and you see that finally okay, that's how it will happen. So whenever you get a slope of this kind, or rather shape of this kind, where from a point it spirals into another point, then we say that the system is stable. So whenever there is a spiraling inwards, it essentially means that if you were to look at the time domain profile, and if that was, let's say that is a 0 in this case, and 1 0. So essentially it will come from 1 0. So it will essentially oscillate. Oops. So essentially what it's going to do is I'm not drawing for this figure. Let me just draw for a general figure. So if that was the equilibrium point, then essentially just going to go and oscillate and stabilize there. So that is the kind of system that you'll see, and that is more or less defined as a stable system. Okay. If it was going outwards, then it would essentially be expanding out, and so you would see something of this kind in that case, which would mean that it is unstable. Sorry, it goes outwards. Oh, I have to erase it again. It goes out like that. So that will be the unstable system. So, so what do we understand from this phase plane and phase portraits? Before I go to the biological systems, I don't know if I have.
And so just one more thing, like
Uh-huh.
this alpha would
I
be
don't have.
continuously
Sorry, yeah.
varying, right?
Sorry,
So
loudly.
alpha would take continuous values, right? Not discrete values.
Alpha are continuous. Alpha can be.
So as in like it can go from infinity to 10, right?
Yeah,
So
yeah.
it'll be like then some very, very large number, then like it'll
Yeah,
be
yeah,
continuously.
yeah. That's what. But we obviously in this small space, there will be there will be an infinity of slopes from starting from this vertical line coming to 10. But we can't draw all of them, right? So we just draw the next one that we had constructed, and we know that when it touches this line, it has to have a slope of 10. So it's not really exact because the way I've constructed this, but if I were to draw it by hand, I would essentially curve that line so that when it touches this point here, it will be parallel to this 10, slope of 10 here. Got it? So you can imagine that I'm drawing this, and I'm drawing this from, I'm going to start like that, and then I'm going to curve it in, right? I can't do it because I don't have control over this. Okay, so that's what it's going to be like. Okay, so that's the method of construction.
Again, like, can you explain again, like, how these two lines are being constructed in between the line, the green one is there?
No, so the way you do it is, if you were to draw this, so what will happen is, okay, there's one part which I not mentioned here. So let me see if I can insert a table. Insert. Can you see a table here somewhere? Yeah. Oops, where it happened? Insert. I want 3 columns. The number of rows maybe 5. Let's go into this to use that here. Okay, so I'm so what's going to happen is here the first column will be x1 because that is your independent variable, right? The next one will be x2. Okay, and you'll have alpha. Okay, I'm going to write as a. So this will be, let's say, a1, 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 a1. I'll continue this, as much as I want. So let's say I'm giving an example of 3 of these, or 4 of these. So if I take x1, 1 as the first point, x1, 2 as the second value, x13 as the third value. Then when I put alpha equal to 1 and I solve the equation, then I will get for alpha equal to a1 or alpha 1, I will get, based on that isocline equation, I will get x21, x22, oh sorry, this is x13, x23, okay. I could also go on till x14 and x24, right? So that will help me to kind of get this line, okay. Now I've drawn this as a linear line here, but sometimes this line is not linear, as we saw in the previous case in this one, right? We saw that these lines are not linear.
Yes, sir.
Yeah. So this
Yes,
will
sir.
help you to plot.
Yes.
This will help you to plot that line. So x1 versus x2, by just drawing the corresponding points, you can just draw a line through it, and you know that on that line, the way the actual system portrait will intersect will be at a slope of alpha 1. Likewise, I can do this as alpha 2, alpha 2, sorry, alpha 2, alpha 2, and I can treat like this, and I can write this one. I can say here I can say again I can take similar points. I mean, so it's not, it can be the same points, it can be more different points. It doesn't really matter. The values could be something that you can choose, but let me just say that I'm taking different values: x15, x16, x17, and I'll 7, and correspondingly I'll get x2.
Yes, sir.
Got it right?
But
So
this
you're
I'm
getting the idea.
understanding, like the thing is that like you have a green line in between.
Yeah,
That
yeah. So
green
now,
line is being
okay, now
constructed. There is
right,
two small line segments
yeah,
besides that.
yeah.
Yeah,
So
those two are.
correct. So what I'm saying is now, so you know how I've got this. Now you would know how I've got this alpha equal to infinity and alpha equal to 10.
Yes, sir.
So
Yes,
I
yes.
know the initial point, and I know that the initial slope is negative, so it is going downwards, okay, from that point. So this point is 1, 0. So this point here is the point 1, 0, okay. This point here is the
Yes,
point
sir.
0. So from 1, 0, I know that the initial value of the slope, that as it touches this point 1, 0, is going to be infinity, that is going to be vertical. So I draw the vertical line here for this first dotted line, clear?
Okay, sir. Okay, understood,
And
sir.
I know that when it comes to this line here, which has this line equal to alpha as the slope, then it's going to intersect this line at a slope of 10, clear? So I draw
Yes,
from
sir.
this point a slope of 10, okay? Now, because I am illustrating this and I'm not doing it by hand, if I was doing it on the board, I would have done it differently. So the way I would do this is that now I know the boundary between which my line will come and intersect this line. So if I start at this point, I know that it cannot cross this line here, and I know that here on this side it cannot cross this line. So I start off at minus infinity, and as I cross over here, I should have it parallel at this point, just at this point of intersection with alpha equal to 10. The slope should be parallel to this line that I've drawn as 10. But here, of course, it's not, because I didn't do it that way. I mean, I just draw it as an illustration. But if I were to draw it by hand, I would just curve this line so that at this point it just becomes equal to 10. Just at that point it becomes 10. So it will become, from infinity, it's going to come down. Let's say from infinity, somewhere in between will be 100, maybe a slope of 100, then maybe a slope of 50, then slope of 20, and exactly when it touches this, it becomes a slope of 10. Got it? So it will be a gradual changeover from infinity to 10. That's the way the slope will change. Clear?
Yes, sir.
Okay. And then at this point, now I know. So actually, really at this point, if I were to draw it, it actually essentially should be that it should be, this will be straight like this, right? So I should draw another line which is slope of 10. Now I know that when it intersects, this is going to be a slope of 3. So it cannot cross this value. So now I know the boundary between which this line will come and drop on this line. And then from 10, I will now gradually change it to a slope of 3 when it touches this line. Clear? And then I continue this process,
Yes, sir.
and until I get this complete curve drawn. Clear? Okay. So there are examples of this in the text, but I will not go there now. I'll just go back to the MATLAB. We'll do these examples later on. and kind of show you one example that I had done. So I'm going to close this PowerPoint. I'm not going to save it, obviously. And I'm going to bring back this one. So there is this one there, this one here. So this is a different one. So fine. So let me just show you once again. So you go to Simulink, and you can do many things. You can have subsystems, you can add projects, you do the whole thing, and many other things are there. So anyway, but this is the simplest and easiest thing to do. So you say that you're going to start a project, a model. So when you do a model, then you get a panel like this, and then you can go to the library. So, and there are many different components here. When you come to the continuous component here, you can pick up a system like this, and you can draw it here, and this will give you this one. So you can copy multiples of this. So and if you just click on this point here, and then click on that one, it should just join. Okay. When you open this one up, you can actually see that there is a panel here which you can use, and you can change this, and I can see that this is equal to 2. And if I apply, then that becomes 2. And I can also do this here, and I can essentially flip this, and I can say flip the block. It changes direction like this, and I can just click on this and click on that, joins it, click on this. But before I do that, sorry. So I have to now, because I'm doing a feedback system, I'll have to go to common math operations, and I can do an addition here. Maybe I pick up this one and put it here. Wow, and then bring it here. And I can, so from here, and you can pull these, you can actually format these a little bit just by pulling it aside. Oops, just put it around. You can open this, and you can change the sign here. You can add more signs if you want to. So you can change the sign here. So that becomes a negative feedback. And I can say that I want a constant step change or something like that, maybe. So I can go to a source, and then I can pick up a step change and bring it here. Oh. And that would be my step change there, and I can make this a 3 maybe. Okay, apply, and I can use a sync, and I can choose something to report something to me and bring it here. Oh, I keep thinking that I've copied it. Bring it here. All right, and all I do is just say run. I don't know, just doing it. It is doing something. Completed. So it's not. It's still doing it. So what? Where it is? Still not done anything. See, so that is the response that you get for this one. Okay. So you could go and construct your own systems and then see how they are all responding based on this kind of behavior. So you can build much more complex things, and I'll show you, because time is running out. I'll do, when I come to the next class again, I'll show you one more thing that needs to be done, where because this is at a very rudimentary level. When you just start playing with Simulink, you can just do a few things like this. So go back and see, and I've done one work on the stability. Maybe I'll just show you that. If it is here, I'm going to close. There is my desktop tool here. There is a Van der Waals oscillator that I had done earlier. So I run this. Should be plotting. Why is it not plotting? I think it's taking time because there are so many things open on this laptop now. So essentially, it will give you a plot like that, something like that. I don't know why it's not doing it. Maybe run it one more time. Continue. Maybe it got stopped. Yeah. So that's a plot for the oscillator. Okay. So the way you do it is essentially you go into this, define a function, and I'll talk about this in the next class once again. So what happened? Open. So you see, I put the Van der Waals oscillator here, where A is the parameter, and A is 0.2 according to the problem that I've been trying to do. But there's another parameter K, which essentially is in front of this. And obviously, if it is 1, then you'll get exactly what I've shown you on this plot there, but this is 0.1. So there's a little bit of skewness that takes place when we are plotting this. So you can play around with this, and we'll talk about this in the next class and how to use this. Okay. So any questions so far?
None currently, sir.
So all of you are okay with this? I don't know. Where am I now? I can't find you guys here. This one. Who's that? So have I been kicked out of this movie? No, I'm still there. So where is the screen that I can see? I can't see you people on my screen.
So probably it's
You
the
can join this meeting.
Okay, no. I'm
Yeah,
in the meeting. Yeah,
this.
I'm in the meeting. I know that. So it's just behind the screen. So anyway, so what we are doing is we are essentially seeing the methods which you can use very easily, and I'll just, I mean, you could do your own coding, but I'm using this so that there is a illustration and a connection with what we're going to do in terms of gene regulatory networks. You see the advantage of using this as at least the first step to investigate something that you want to look at, because you can do this very quickly. And then of course you have to do some advanced coding when you look at very large systems. So with that, let me end this class. And anybody has a question?
None currently.
Okay, all right. Take care. Bye for now.
Thank you, sir.
See you later. Oh, I will not be
Thank you,
here
sir.
for the. There's no. Hold on. There's no class on Friday because I'm going out on gate duty. I'll be out of station taking gate exam. Okay. So
Okay, sir.
that is being postponed. Please let everybody know on the WhatsApp.
Yes, sir.
Fine.
Thank you, sir.
Okay. Bye.
Thank you.
Bye.